So let's start with a bit of history of photocatalysis. So it all started 50 years ago in Fujishima's PhD study. He and his supervisor found that water can be decomposed by a titanium dioxide electrode with a very strong light illumination. This phenomena is called the Honda-Fukushima effect. And right after his graduation, he and his supervisor delivered the world's first solar water splitting device. And they published their results in the Nature journal. Now let's take a look at their prototype. As you can see from the left side, we have some light absorbed by the semiconducting TiO2, and some of the electrons can be extracted or jump into the conduction band, and these high energy electrons will be transferred to the cathode side by a biased voltage. And these high energy electrons can reduce the hydrogen protons to generate the hydrogen gas. So besides hydrogen production, photocatalysis can do a lot of things like pollution degradation, disinfection, carbon dioxide conversion, and also nitrogen fixation for fertilization. So over past 50 years, the solar to hydrogen efficiency improved from about 0.01 to 20%. This is a remarkable progress. However, there's still some remaining issues, such as lack of stability, and the structure is quite complex and quite complicated, and it's not very easy to make the large-scale production. So all of this leads to some, the overall low production and very expensive cost. So now let's take a closer look at the production and the cost globally. So on the left side, we can see this pie chart. We have data from the US Department of Energy in 2020. We can see that still over 98% of the hydrogen productions from the fossil resources, which is a very, not carbon-free and pollute the environment. And only 2% of the productions from the electrolysis. But electrolysis can be either clean or dirty. It depends on what kind of electricity you're using, right? If it's from solar, hydro, wind, they're okay. Otherwise, it's going to be not that clean anymore. And regarding the the photocatalysis, it's very pathetic. It's only, I would say, way much less than 0.1%. Regarding the cost, we can see that if we use the natural source to get the hydrogen gas, it's just about more than $1. However, if we use some solar-related electrolysis, the price is gonna be escalate like from $6 to $12, and let alone the photocatalysis is gonna be way much more expensive. So why do we still need hydrogen gas or energy? Because we need a green future. Both North America and Europe, they issued or developed some plans to cut the carbon dioxide emission. The near goal is by 2030, the emission can be cut as half. And what can hydrogen do? It can do a lot of things. It can replace a lot of current energies, like we can generate the electricity by using the hydrogen gas, and the only product is water, so it's super clean. And also, it can be used in a lot of industrial scenarios. And also, of course, everybody knows that it can fuel our cars, vans, semi-trucks, trucks, even some yachts and ships, okay? Regarding the cars, I think the hydrogen cars are going to be the future, because hydrogen has a very much better fuel efficiency. It's about 3 times more efficient than conventional gasolines with the same weight. And also with some fuel cell technology improvement, we can also have very good efficiency conversion from hydrogen to electricity. Okay, they're going to be all used in the vehicle EV industry. All right, now let's take go back to the material side. So how can we split water? The metal doesn't work because they don't have band gaps, but they can be somehow helpful in another scenario. I'm going to talk about it afterward. And insulators, no, they have two broad band gaps. So as TiO2, we know the semiconductor works. They can do the job. And here I want to point out one thing, that is the band edges have to straddle over the oxidation and the reduction potential of water, which is 1.23 electron volt. So besides TiO2, which other semiconductors can do the jobs? There are a lot of choices. There are a lot of semiconductors have the suitable band gap size and positions. But however, some of them will not be working because they will suffer very severe photo corrosion problem. So if we are interested about one specific semiconductor, how do we start it? We're going to use the help of DFT, right? Density functional theory. We can calculate a lot of things like band structure, transitive states, optic properties, some couplings, phono dispersion, and ST emission. So, but anyhow, since I don't have time to expand on this topic, but I know audience are you are the expert on this topic. I'm not gonna expand it here today, but I do like to show some essentials and some terms here. And one thing I have to point out is that it's very related to my topic today, the band gap. DFT is amazing, but everyone knows that it has a lot of, still has a lot of issues. And the one thing related to my topic is that DFT underestimates the size of the band gap of semiconductors. It's because of it always delocalize the valence electrons and also over stabilize the metallic ground states. So there are several ways to compensate or circumvent this problem. And one solution is using the Hubbard correction. It's also known as DFT plus U or something plus U. Here I give you an example about this DFT plus U results. As we can see from this band structure, we have a band gap calculated like around 2.3 electron volt, which is very close to the experimental measured one. But if you take out the plus U method, you're gonna use the pure DFT. You're gonna only have 2.1 electron volt, which is significantly narrower than we want. It's not good for our study, since we want to engineer the different combinations of materials. Okay, and I don't have time to expand the way how to do the Hubbard parameters. You can check it or Google it or GPT, whatever thing, afterward. So now we know that how to calculate the band gap size. In particular, in the case of TiO2, we have this 3.2 electron volt. So let's see how efficient it is. It's not efficient because it has very large band gap. It can only absorb the light in the UV part. But we know that the UV part is just 3% of the whole solar spectrum, leaving 97% of the solar light wasted. So this is why this topic hibernated or paused more than 30 years. So in the last 2 decades, people found that by putting metals on the top of the semiconductors, they can build some Schottky junction to help the semiconductor to take out the electron to the conduction band. And another thing is, since this metallic thing will have something called surface plasmon resonance by changing their morphologies. Essentially, the SPRs are just electromagnetic wave-driven electronic oscillations. Okay, so by using this SPR, we can both extend the range of the photocatalysis. Also, we can have these hotspots. These hotspots can have a very much enhanced field enhancement, which can significantly improve the mobility of hot electrons. All right. So here I show a few metals and their absorption range. And now, since we want to shift our perspective view from the atomic size to the nanometer or micrometer size, because we want to reshaping or engineering the shape of plasmonics, we're going to need the help of you can call it photonic simulation or electromagnetic simulation, the same thing. And this job can only be done by it. The DFT will not help. Okay. So here I show a few simulation methods: FDDD, FDFD, FEM, and etc., and some software. So using this software in last 2 decades, people put their endeavors to extend the active range and the field enhancement by engineering the morphology of the plasmonic nanoparticles. One typical method is just to put 2 metallic particles together closer. We're going to have some hot, something like a nano gap. This nano gap will provide you very, very strong field enhancement. And another strategy is just make it a bit longer. You can have extended absorption range, and also you can make it more exotic. You put more like star here. You have more numbers of the hot spots. Okay. And here I want to show you that the people in Ohio, United States, I think in Alexander Gavril's group, they developed a way to extract the hot electron generation rate or transferring rate from this numerically calculated part. By putting this numerically calculated part to this beautiful equation, you can estimate the hot electron distribution and the hot host distribution. So before us, people were focused on changing the morphology to improve the SPR part, metallic part. However, the possibility of creating resonant cavities inside of the visible IR transparent semiconductors has long been overlooked. So in 2016, we showed that we can engineer the shape of the titanium dioxide, and we can build the WGM, the whispering Gary mode, inside of these TiO2 spheres. So as we can see from these simulated and analytically solved results, first thing is they match very well. And if you are first year student who does the numerical simulation, it's better to get the job done, and they are very matching with analytical results. It can build your confidence and also make sure everything you do is correct. And you can see here, we do have some low order of WGMs kick in, and it will improve the provide additional hotspots like here. There's no metal, only the dielectric thing. Now we can put the metal outside of the interface. We check that by increasing the size of TiO2, we do see both from simulation and we did see from both simulation and measurements. By increasing the size of the TiO2, we have more absorption. Also, if you check the near field distribution, we can see that the largest one has the strongest field enhancement. Quite interesting, right? So we also studied that by inserting the gold particle into the interface of TiO2, we can gain additional extended active range. Also, the overall absorption in this visible range can almost tripled. And my friends also, chemist friends also, they introduced this Janus system. Essentially, they are just the dimer thing I mentioned in previous slide. With the dimer, you have extended absorption peak, and also you have way much stronger field enhancement here. And you can see a bit animation here. Then we sent our designs to our collaborators in Sherbrooke University. And to make a long story short, we can check the final figure here, the hydrogen evolution. We can see that the Janus, the dimer structure with WGMs participated, has the strongest or most prominent hydrogen evolution efficiency. Okay, you can also see from the absorption and IPCE measurements. And in 2020, we also did another follow-up work. We built WGMs inside E. coli bacteria. My collaborators, they are very cruel people. They just replaced the shell or skin of the E. coli bacteria by TiO2 titanium dioxide. Then they spread gonad particles on top of the surface of the bacteria. Then they also grew some TiO2 fibers on the gonad particles to offer additional hotspots. Now, let's take a look at my numerical analysis. We can see, at first glance, we can see, check this figure, we can see by adding more TiO2 fibers, we do have more hotspots, and also we have WGMs, lighten up all the gold particles to enhance it. We can check also the enhanced and absorbed analysis here. Then again, they are measured by our friends, collaborators. We can see that the final structure, this complex one, has the best, the most prominent result. So here comes my perspectives a bit. Other possibilities to improve the photocatalyst design. So the first thing I want to mention is the topological photonics. It allows you to build some devices having very good defect tolerances, And also last year we found that these artificial atoms can be reshaped in terms of the morphology. This is not going to happen in the electronic structure, right? Another thing, we can introduce the strong coupling, strong light-matter interaction. It can either extend the active range or modify the reaction potentials. Very interesting. So artificial intelligence is quite hot and trendy stuff. It already has a lot of things to do in the photonic world and also photocatalysis maybe. And here I just present you two examples to, like these ones in general photonics and these ones for topological photonics. I think they're going to be very helpful to build some AI-built photocatalytic systems without intensive computation. And this is my last slide. I want to mention you some computational path to study the photocatalytic systems. The first thing you want to do is just study and check what kind of combinations of materials you want to use. So you're going to do the DFT calculation. Once the materials are fixed, you can design the real devices. Something can make it larger and utilize some optical concepts to make it more efficient. Here I just present some of our works here. And the last step, if you want to do something more, like if you want to check some temperature dependency, microfluid, and something like expansion, you can think about multi-phase coupling. In the end, you can also do the chemical engineering numerically. So I think everybody wants to see this last slide because everybody's hungry, right? Okay, cannot wait, huh? Yeah. So I present to you that the importance of using the photonic simulation to do the photocatalytic design. and I present these two devices, and in the end, I just showed you some perspectives and seeing that photonic simulation can be very helpful to extend the active range and also make everything cheaper and make everything stable. So that's it. Thank you for your attention.
So you can see there's a breadth of different sorts of simulations and computational analyses going on here at INRS and the neighboring universities. So are there any questions related to this talk?
So I might have missed the point, but why did you remove the skin of poor bacteria and put the gold nanoparticle and titanium dioxide on E. coli?
The gold particle.
What is the role of bacteria?
Oh yeah, I maybe went through it very fast. So, because yeah, as you can see from here, right? This figure B. Let's say that this is a bacteria, right? Without any fur, whatever thing. So I told you that our collaborators replaced the shell of the bacteria by TiO2. So now it's TiO2 shell, not bacteria shell anymore. Yeah, we killed them. Yeah, yeah. We use that to build a whispering gallery mode. Then we have this hot spot. Then we put on again the hot spot, the gold particles. Yeah, to further improve it. It's kind of multiply. Yeah.
I have also a question. What is the field strength that you have when you have those plasmonic structure? What's the
field?
The field strength.
Field strength. What's sorry? I couldn't understand.
So volts. I mean, you are focusing the light, which means that you are enhancing the local field strength. So
yeah.
What values do you reach?
You mean how much was the field enhancement?
Yes.
Okay, yeah.
Well, but in volts per meter, if possible, because dBs don't, for me, don't mean.
I see. So for this E. coli bacteria thing, you can see from the simulation, it cannot be measured. So from the simulation, we estimated like 400. And for the previous one, I think I didn't show, but I think it's in some hidden part. Yeah. Yes, I didn't show this slide because I don't have too much time to spend. So in the first case, the field enhancement is really impressive. It's 4,000. Yeah.
Thank you.
4,000. Yeah. Thanks. Yeah.
Great. So let's thank our speaker again.
Thank you.